This is the part 1 video podcast for Field Methods in Hydrology, Chapter 11, related to surface sediment sampling and measurement. Surface plays an integral role in hydrology, and that's because water is stored in it, water flows over it and through it, and then sediment and water work together to create habitats for organisms. And sediment records important historical information about past hydrological events. So we can use the record in sediments to reconstruct things that we couldn't have observed. And that's particularly important when you're going back through long periods of time. Sediment also plays a very important role in society, although it's totally not recognized or appreciated as such. But billions of dollars are lost every year as a result of sediment moving around on the landscape from where you want it to where you don't want it, or simply a lack of sediment, too much sediment. Just like with lack of water, too much water. It's just a fundamental problem that a society has to deal with, but it's a very challenging problem because it's just not something that people think of as important. So in this chapter, I want to address the basic properties of sediment, where and how much sediment you should get, how do you go about collecting sediment samples, and then in part 2, which I'll do separately, that's going to cover erosion and deposition measurement methods. When you look at sediment, and here I want to focus on surface. So, sediment, of course, comes as a deposit usually. It could be soil that's formed over thousands of years, or it could be relatively quickly deposited alluvium or colluvium. So colluvium is sediment that's on hillsides and creeping down hillsides, and alluvium is stuff that has been moved by water, typically into a river corridor. So when you look at the sediment, it is layered, it is textured, in terms of the composition of what's there, sizes, colors, materials. But I want to focus more on what's happening on the surface, and then there'll be a separate presentation later on with regard to subsurface sediment and drilling wells and coring and things like that. So some of the basic properties that we're going to be looking at are the grain size distribution, color, and organic content. There are many things that one can pull out of sediment, and people are just remarkably innovative in terms of finding new things to measure all the time. We're going to focus on the essential things that you should learn how to measure as part of being a professional hydrologist. When we talk about grain sizes, we want to know what is the size of individual grains, what is the size of the bulk medium itself, and we can think of those sizes in some very simplified groupings of sizes, which I'll show you in a moment, but typically we think of that as gravel, sand, silt, and clay. And the main reason that we focus on grain size is it tells us a lot about the ability of water to move through that material or over it. We talked about, with the open channel flow, the idea of roughness and Manning's N and the role of grain size in that. But in groundwater flow, we have hydraulic conductivity, and it's largely determined by issues related to particle size or grain shape and sorting. There are other factors, but grain size is usually the simplest and most important factor that people tend to characterize. Also, if you look at the pattern of the sizes that are there, like if you look in this photo, you can see distinct bodies of sediment in here, which people call packets or strata, and they are representative of different hydraulic conditions that led to the deposition that you see there. So trying to reconstruct what those conditions were can be very important, and so being able to characterize those sediments as a first step, and then understanding the science of what that means, which is a part of the geological fields of sedimentology and stratigraphy, then you can really make a lot of headway as a hydrologist. The most predominant way of characterizing particle sediment size is using this Wentworth size scale. So if you look at the far left of this table, it gives size in millimeters starting from the largest down to the smallest. And then it also gives it in micrometers, 1 times 10 to the negative sixth meters, because sizes start to get really small. And the first thing you can see is particle size does range over many orders of magnitude. And as a result of that, it's quite common to use a log 2 scale. Not a log 10 because it doesn't vary by 10 times orders of magnitudes, but typically just log 2. And the log 2 is given here in the second column. And then over to the far right are some very simple classes of particle sizes just to put names to these. And so typically we have clay, which is here at this 4 micrometer level. Then the distinction between silt and sand, which is at the 62.5 micron level, and then sand to gravel at 2 millimeters. It's also quite common to hear the term mud, and although that's just a term a lot of us could use, but scientifically we think of mud as the totality of silt and clay. Unfortunately, the term fine sediment can be used to mean many different things. If you work in a gravel cobblebed river, fine sediment usually means sand. However, if you work closer to the ocean, then fine sediment is usually going to be mud. So that's some basic sizes to be mindful of. So if you're familiar with the pH scale, then you can understand phi, and we'll cover pH if you're not. But it's just the idea that using this log 2 scale, you're taking numbers that are going over many orders of magnitude, many decimal places, and you're simplifying it down so it just goes from positive 14 to negative 20. Now the next thing you may wonder is, well, why is the largest size negative and the smallest size positive? And the answer is just simply human preference, because most of the sedimentologists were working with very small particles. They didn't want to work with negative numbers, so they made smallest particles a positive value, and then the larger particles a negative value. So typically what my experience is like people who work in very coarse sediment tend to not worry about phi and just talk about the positive sizes, whereas those who work in small sediment do tend to use phi because it's positive, because we all like to have positive values. Another property besides just the size of particles is the sorting of the material. And here are just 4 different illustrations to show well sorted versus poorly sorted. Now the number one interpretation with sorting is how quickly was the material deposited. When material has a long time to be distributed by water, it tends to be segregated as a function of size, and that leads to very well sorted material. It also depends, of course, on the supply. If the supply is already well sorted, then it isn't going to be an indicator of speed, but just an indicator of supply. However, we typically think of something like a debris flow where you're getting a lot of material from hillsides and hollow colluvium and first order channel alluvium. All the material goes down a river and then quickly deposits out. You would see a very poorly sorted jumble like in the lower right. And if we go back to this first photo, you can see some layers in here that are poorly sorted, where you have large particles, but they're not necessarily in contact with each other. They're being supported by the finer material. And then on the top here, you also have poorly sorted, but it seems to have a higher abundance of large particles. And then in between those is a very well sorted layer of sand. Another aspect of surface sediment that you might want to describe would be color. And color isn't going to be so important for inorganic material, but if you have organic material and say soil that has been subjected to chemical weathering that has been producing soil through time from that parent material in the sediment, then you do tend to see color. And we can use this thing called a Munsell color chart to take our qualitative interpretations and give them a specific numeric value to that to help provide repeatability in that interpretation. But the most important things we're looking for here have to do with the presence of oxygenation or absence of oxygenation, or other things that tend to cause a change in color. And another one would be iron and manganese, which can, just like oxygen, play a big role in the oxidation state of the sediment. So that's the key thing, is looking for organized structures like models, or looking for discolorations that indicate wetting and drying, which then tend to indicate having oxygen or not having oxygen, whether you're exposed to the air to get that oxygen or just stuck in the water or deeply buried in the absence of oxygen. Organic content is a very important property of sediment because a lot of material could be coming from litter or other surface debris, and organics themselves can be useful for environmental analysis, like figuring out, okay, if I have a lot of charcoal, maybe that's telling me about fires. If I have wood fragments, it might be something that I could use for radiocarbon dating. Same thing if I have seeds or other, even like insect parts. I mean, all kinds of things. People are just amazingly expert at understanding very specialized aspects of what's in sediment. So that can be very useful. But just at the most basic level, if you smell the sediment and it smells like it's rotten egg, then it may be an indication of a lack of oxygen conditions. You also may have an indication of the presence of sulfur. As sulfur is oxidizing, then you can get a smell. And if we take a fraction of sediment, of course, weigh it dry, and then burn it in something called a muffle furnace, where you can put it at like 450 degrees Celsius for 8 hours, weigh it again, and then the difference between the dry weight and the burned weight is going to be the volatile organic content. A more sophisticated approach would be to use a carbon analyzer, but the basic thing that is very commonly used is just loss on ignition. Okay, so those are some of the basic properties of sediment, to just give you an introduction to that. And we're not doing a laboratory class here. You will have a little bit of chance on homework to analyze some grain size data, but the focus here really is on the field methods of sampling. And as part of the stream assessment video podcast, I did talk already about surface texture assessment and spatial sampling. So I'm not going to repeat this, but I just have this here as a reminder to you, whether one wants to use an equal effort to really represent each individual strata very thoroughly, or whether one wants to use proportional area sampling so that you can get, have a good map. Like you might have a lot of samples in areas where there's a lot of that kind of thing. So you just have to think through whether your goal is to get the numbers that characterize the strata, or whether you want to do more kind of mapping for what you want to get out of it. But in terms of how you go about that, then we're going to look at the different methods of sampling and put our focus there. And this also is just a reminder to me to talk about, very briefly, how much sediment you need. Well, how much sediment you need is going to be a function of the size of the material that you have and the size of the grains that are there. Well, I guess that's the same thing. Sorry. Basically just the size, okay? So, for example, if I have rocks that are the size of my fist, and each rock is 100 grams, let's say, I don't know, then you can't just collect 100 grams, right? So it's a question of how many grains do you want to have, and that's going to be controlled by the largest size. So I could have a sample that has mud and gravel. Well, the mud, it could be that 1 gram of mud could be, 1,000 or 10,000 particles or whatever. But, 1 gram, of course, isn't even going to equal 1 grain of coarse sediment. So, so in order to get a grain size distribution that represents the mass, you have to sample enough of the largest particle size, which means you have to generally dramatically oversample the finer sizes. And now we're just back to the same problem like in this spatial sampling, and the difference between representative area versus representative or equal effort. We have to achieve an equal effort for the coarse particle sizes, and that means we're going to have to dramatically oversample the finer material when you go and get some sediment. Well, we can just look at the simplest method. I mean, a lot of times if you want to just get material of soil or in a stream, just get out a shovel and dig some out. Just remember, if you're going to do it this way, you're not getting that very surface veneer. So if you want to know what is like controlling the roughness of the ground surface, or just having that superficial substrate characterization, a shovel is not going to be a good choice. Shovel is going to give you the bulk material, and it's going to be destroying the structure of that material, but it is going to allow you to get at it. So, shovels are fast and cheap. Of course, you can have a hand shovel or a large shovel, spade or pickaxe. So just think about that. And I mean, the cons here have more to do with some of the well digging side, but in general, shovels are just pretty crude, blunt instruments for soil sampling. For our homework number 2, you got to use the brass ring. So you just take a ring and then pound that into the ground. And if the material is at all cohesive, then you can collect that ring and really get a reasonably well preserved sample. It may experience some vibration, but you can try to do it as carefully as possible to retain the structure and integrity of that cylinder of sediment. The compliant cavity is an alternative approach. Dig it out with a hand shovel or something, and then you can put saran wrap into the hole, pour water over that, and see the volume that you pour in divided by, so it's the mass of the material you extract divided by the volume of that material gives you a bulk density. So these two are both sampling methods, but I'm just putting them here also in the context of measuring bulk density. And we'll come back to the bulk density as a parameter primarily when we talk about vadose zone hydrology and its methods. Okay, so let's get to the meat of how you would sample sediment in streams. And it's going to hinge on how coarse the material is. For relatively fine-grained material, and so this might be sand, silts, and clays, then a very typical approach to use from a boat would be a Ponar grab sampler. And I'll show you this, of course, in person, but what you can see here is that there's this pin that's in here. Well, if I take that pin out, then there's like a scissors mechanism here, and it's actually very gently resting on top of each other. It's like a pressure fit so that it stays in this open position. And so when that goes down, when you lower this by a cable, then you drop it, and it goes and it hits a river bed or a lake bed or estuary bed or whatever, then what happens is that this actually compresses in, it kind of squishes in, and that unlocks it, and then when you pull it up, it just snaps shut. I'm not explaining it very well. That's why this is a field methods class and why we're going to play with this stuff in class. But a Ponar grab sampler just gives you a bulk material. It's your typical clamshell, go in, close, and come up, and have a sample of material. A little bit more sophisticated approach are these bed material samplers. BM is for bed material. The number is the year that it was invented, so 1954, 1960. The 54 one is a really big one intended to be used off cables. BMH is like handheld. It's on a stick. It's still really heavy, but it's a little bit more manageable. And so this has a spring-loaded device in here. So what you do is you push this down, and when it hits the bed, it's going to snap, and that's going to cause this wheel to cycle through, and it's going to grab a sample and be closed up inside into here. So something like these more official bed material samplers are things that you can find at this company, Rickley Hydrologic. They have a lot of industry standard stuff, and I'm not advocating for anyone. I mean, but it's can be hard to find sediment samplers, so I'm just trying to point that out to you. Okay, coarse grain sediment, again, you can use a shovel, but when you're getting into gravels and cobbles, everything is just heavy. There's lots of it. And the big problem with a shovel is as you're digging stuff out of the top, then material just starts falling back into the hole. What you'd like to do is have some approach of taking more of like a core of material in the near surface zone, like the top 15, 20 centimeters. Um, so you want to retain the integrity of that hole. And what this is a McNeil core and McNeil sampler. You can see in the photo that there's a handle on this thing. So you just grab this thing and like you kind of just wedge it in and rotate it in like you're driving the steering wheel of a car. You jam that in and rotate it. You can have little teeth at the bottom if you want. And once that goes in, then it's this tube, 10 centimeters in diameter, that is the sample that you want to collect. So then you just reach in, like you see this guy is hunched over. He's not in it right now, but you reach over and you pull the material out of this tube and you put it out into the larger bucket or basin. And then you can just cap this and then pull the whole thing out of the bed, and your sample is what's here in the basin. And then you can pour that into a bucket or sampling bag or whatever you want. So this is a device that allows you to get very coarse material from a very focused area of the riverbed. And both the McNeil core, Ponar sampler, bed material samplers, these can be used on the land too. They're more commonly used in water, but it doesn't have to be that way. Another thing that is a very common method that's used for surface sediments, and again, whether it's underwater or not, just doesn't really matter. But if you have generally gravel or cobble or boulder, then there's a method called the Woolman pebble count that's used for getting the surface texture, by which we mean grain size distribution. It's a way of basically getting individual grains and then manually assessing the grain size one at a time, and doing that for like 100 to 200 individual grains per count. So you still have to have your sampling scheme to decide where you're going to do any of these methods, but once you've picked your spots, you can either lay down a square grid, and so that could be like a 1 meter wooden square, like imagine a meter stick and have 4 of them to make a square. And then you can run strings across that in 10 centimeter intervals, or you could make it even bigger than that, but basically making a grid that you can lay down, or you could just lay a tape down as a transect in the stream. And then there's many different ways of how to pick the individual grains, but by whatever method, collect individual rocks on the ground at each node or line mark. So for example, let's say you have an individual tape and you lay out a 30-meter tape and you say, I'm going to get 1 grain every half meter. So you'd be looking at exactly what grain is hitting the line of the tape at that half-meter mark. Alternatively, you can just roughly go to that interval, then like put your eyes up or close your eyes, take your pinky, put it behind you and bend over, and whatever the first particle is that your pinky hits, then take that regardless of its size, pick it up and analyze it. It's a little problematic because when you have grains, you might have a larger grain and a smaller grain, and the larger grains might be poking up higher. So when you put your pinky down, you might hit that preferentially. On the other hand, a large grain can be embedded, and so therefore it's not always the case that a larger grain is going to be sticking out. But there is a risk of bias, so it's not so easy to do. Once you've picked up an individual rock, then how do you measure its size? Well, the old way used to be to take that rock and have either a ruler or a caliper and literally measure that. But what do you measure and how does that work? So if we look at an individual rock, and I actually have one here, but you can also see this ellipsoid on the screen. An individual rock has 3 axes. It has the long axis that you can see in this ellipse. It has the second biggest axis, which in this case is transverse, and then it has a skinnier axis, which in this case is up and down. Now, I'll try to show this with this individual grain. This is the skinny axis, okay, the up-down. This direction, the up-down is now the intermediate axis, and then okay, wait, I didn't show that well. Okay, okay, so for up-down, let's do up-down. This is the long axis. Okay, okay, up-down is now the intermediate axis, and if I go like that, it's the skinny axis. Okay, so those are the three. Let's try it one more time. Longest axis, intermediate axis, skinniest axis. Okay, so that worked. Now, why does that matter? Well, we would like to know the size of this grain. So what the heck am I going to measure? I mean, and this is it's a smooth ellipsoid, but it's pretty standard grain. Well, here I have a square hole, okay, and I want to know if this grain is going to fit through this hole. Because a square hole is the standard thing that we use for what we call a sieve, and I'll show you a sieve in a moment. But how do I decide what size this is? Well, I need to either take a ruler and measure the axis or figure out what it's going to fit through. So let me take the largest axis. I'll stick with my vertical orientation. That seemed to work. If I try to put that in here, it won't fit. It's just a little bit too big for this hole, so it doesn't fit. Now let me look at the shortest axis. Okay, well the shortest axis, of course, the shortest axis is going to fit through, so no problem. But what's really governing this, I don't know if I can show this very well, it's the intermediate axis, which in this case is left to right, or if I, well, okay, this isn't working. It's the left to right, the intermediate axis. Okay, so the vertical now is the A-axis, it's too big, but you can just see that if I turn it this way, that now the horizontal axis, it does fit. The fact that the vertical axis right now does fit, it's irrelevant because it's too small. And so you can see in that silly demonstration, just call me Beaker, I guess, that silly demonstration, the intermediate axis is the one that controls what it's going to fit through. So it might help to just cut out your own little piece of cardboard and cut out and get yourself a little rock out of the yard and play with that and convince yourself of that. So you need a way to measure that intermediate axis. Traditionally that was done with a caliper, but I'm going to show you why that's not such a good idea. And then you're going to record those sizes and repeat that procedure. And typically that's repeated 100 times so that you have a pretty good representation of the particle size distribution. The problem with rulers is that even with a ruler, people have a lot of trouble measuring grains because grains have, complex shapes. So on the left is an experiment in which we have a number of different sites B6, B4, like people went out to a stream, and then at these sites they were asked to measure the grain size of that site. And the value on the left shows the median grain size, D50, right? The 50% of the material is smaller, 50% is bigger. The median grain size that many people measured. And each person measured their own median size, and if we take the distribution of what all the different people got, then the square shows the average value, and then you can see the range and outliers for that. And there is a pattern here where as the size gets bigger and bigger, you generally have a wider range of what people identify as the median size. And then this other plot on the right shows D84, which is the particle size that 84% of the sediment is smaller than. And it's a commonly used size for representing the framework, like the large particles that are holding the whole thing together. And so what you can see is that within any individual site, 10 different people will yield a variety of different estimates of the grain sizes of those sites. Another experiment is the effect of a ruler, where if I have one person measure samples and see, can they repeat the same result? So here's person A, B, C, D, E, F, G, H. what you find is that there's a lot of variation within a person and a lot of variation from person to person in estimating both the median and 80/40th percentile grain sizes. So this study that was published by Marcus et al. In Water Resources Research just shows that there's a lot of problems with the methodology of a Woolman pebble count and as well using a ruler. So one of the solutions to that is to substitute out a ruler with a gravel template. A gravel template is just like what I have in my hand. So it's a single sheet of metal that has pre-cut out squares of set sizes. And mine in my hand only has one. But what you can see here is a dry ground with gravel and cobble. And there's piles of different size material on some black sheeting. And then you see the gravel template, and you can see how the size of the openings can vary, these two different kinds of gravel templates. Gravel templates also come in a round version with round holes, but I don't recommend that because the standard sieves that we use for gravel, sand, silt, and clay are all square sieves. So you should use the same consistent shape as what we commonly use. The last thing I want to mention is just what do you do with sand and silt especially. You have the opportunity to dry sieve it. So instead of putting your hand, taking an individual grain in a gravel template and one at a time pushing through 100 grains, well, what do you do when you have 10,000 grains, right? And they're tiny little specks. Well, the answer is you take a wire metal mesh, usually brass, but can also be stainless steel, and the mesh is designed to have openings that are all of the same uniform size, and they typically come with an 8-inch pan, but you can also find 12-inch pans or 4-inch pans or 2-inch pans, but 8 inches is the fairly standard size. And you create a stack of those, and usually the stack is in a half fee or quarter fee scale. So this would be the point to pause and go back to the Wentworth scale and see what I mean. Like what's half fee, what's a quarter fee? That's the log 2 scale. So fee is the like the equivalent of pH, but for grain size. And so you would stack them with the largest opening at the top and then going down to the smallest opening with a pan at the bottom. And you pour the sediment on top, dry sediment, and then this is a machine that you're going to love. It's called a row-tap. Have you ever done the little fun thing where it's like, can you tap your head and rub your belly at the same time? Okay, there we go. Now I got it. So that's what a row-tap machine does. A row-tap machine takes the sieves and mushes it around, which is the main action of the particles trying to get through the hole. But sometimes the particles get kind of wedged in a mesh and they're stuck. So what the tap does is it makes the grains bounce up and find a new opening. So everything sort of filters down through here and it gets held up on the mesh that it cannot go through. So and then all you have to do is just weigh how much material is in that pan, in that sieve, and as well as what's in the pan that made it all the way through. And that is the mass of material that's larger than that size. And so you can make a distribution on that basis. So I'm going to stop here. We've covered some basic properties of sediment, a little bit about where to sample, how much to sample, and then a variety of different methods for collecting surface sediments. And we'll talk about coring methods and drilling methods for the subsurface later on in the future when we're talking about groundwater. But this gives you a basic understanding of what goes into sampling surface sediment, and we'll be practicing this with the equipment in the lab and also in the field.